Hello, I like breadboards, and to complete my E&L Industry breadboard system collection, I bought this monster one on eBay. It cost $1,300 in 1971, which is almost $10,000 in today's money. In addition to its 4 breadboards, many switches and lights, it promises to have 3 variable power supplies, a full function generator and a pulser. It was pretty banged up, and we had to do quite a bit of electromechanical repairs in the first episode. It took a long second episode to resurrect the power supplies and the function generator. Well, not quite. After much effort and many a transistor change, we finally have a square wave and a triangle wave. But the sine wave is still eluding us, and as you'll see, it won't be the only thing eluding us either. Thanks to Master Ken's reverse engineering, we know that the circuit that produces the sine wave is a sine shaper, lifted straight from the revolutionary Hewlett-Packard 3300A generator, introduced in 1965, which I repaired in a recent video. So it works the same way, right?
So you use diodes and resistors to shape the sine wave. It's exactly the same structure. As the voltage rises, more diodes turn on, putting more resistors into the circuits, and so you get a piecewise linear sine wave. You know, cut and paste the circuit.
Same number of diodes, same differential amp. And there's something wrong with our sine shape here. Okay, I bet you get another dead transistor somewhere. We found quite a few dead transistors in our previous debugging, so my first step was to check the shaper circuit's transistors. A quick in-circuit test with the diode checker found 2 suspicious ones, which I took out for closer inspection. So I took my 2 suspicious transistors out, and once they were in the transistor tester they were fine, so I put them back in. And I still have the same problem with the sinusoid, but that shouldn't be too hard to figure out, right? So if I go on here, well, I should check that my signal makes it in, and then it's ground on one end and the voltage on the other end, so I should be able to check the voltages of the diodes. I mean, this is a simple circuit. And then if the voltage check out, I should see if I lose it somewhere here. Or it could be the voltage supplies that are bad. That could be too. So I'm going to check the 2 power supplies that power the dividers. This one is the red line, plus 3 volts. So I don't know what they should be, but they should be symmetric. Minus 3 volts, and okay, so that sounds plausible. These were these 2 points here, and then if Ohm's law work, they should be all gradated over here. And it's easy enough to check the output. It should be in the middle of those diodes here, so that big line. So we check if actually the passive part is working. Over here, actually the 2 first diodes have no resistors, so it's easy to do. Oh yeah, I have a sinusoid. It's not HP quality, but here's a sine wave. So the divider works, so that's that whole part works. So I must lose it over here, I guess. Okay, so I'll be checking right here to see if it makes it past the first differential pair. And still my red trace here, not sure what level to expect. Oh, it doesn't. Okay, I lose it there. Differential pair not working. One of the 2 transistors has to be bad. And here's our differential pair of transistors that we compare against each other. This is the first one, it's just a decent transistor, NPN. Yeah, they're not perfectly matched. I matched mine closer, so this one has more gain than the other one. But nothing that would cause the stage to fail, so not the differential pair. the transistor. After that, a bad resistor. Okay, mystery solved. It appeared to be the transistor that was after in the chain, and the reason it screws up the pair before it's because it's included in the feedback loop. So the reason that the transistor after the pairs screwed the signal in the pair is that it's part of the feedback and it's DC feedback. So if the level is wrong here, it's going to be biased completely incorrectly. The pair never turned on. So not much info on this transistor except that apparently from the little I found it's a fast one. It's a 400 megahertz transistor. I put a PNP that was one of my better one, 400 megahertz, another one of those HP that has no equivalence, but I have lots of vintage HP parts. Let's see if that cure our last fault. I'm still looking at the differential pair. By the way, I have not changed my test points. Oh yeah, there it is. Okay, so differential pair now is working. That's the output right there. Turn that off. So let me go back to the output and see if we have fixed our generator. That was the last bad transistor. Okay, so we have nothing because I need the 32 volts. And there it is. Alright. Woohoo! Square, triangle, and the sine. All repaired. Okay, so it was just one more transistor. The base move. Okay, this is just beautiful. So this is all the transistors we changed over the two last episodes. You'd think that would be enough, wouldn't you? And I thought so too, so I put the whole thing back together, and then that's when this happened. And I put it all together and I was all happy, and it didn't work, and it started to make a weird noise. And that transistor here is super hot and nothing works, and so something else went wrong when I put it back together. Oh great, our power supply went poof. But there is more. Our generator is not working properly either, and in a very weird way. So dang, the circuit is back on the bench, and I have reinforcement came in. Tube time, and Ken is back here observing at a safe distance. And besides my power supply problems, I noticed that when I went too high in frequency, I lost it in a weird way. So this is the triangle wave out of the integrator, and this is the square wave out of the comparator. And then we looked at the output itself of the comparator, which is right there. And when we lose it, it oscillates, which we thought was strange. There you go. So it's doing it halfway. And then Eric, the master of all magic, tried the magic finger. That didn't work, but then you tried...
Well, we can try the magic finger again, but...
Well, it made it worse. You have an unmagic finger.
Yeah, this is... I should go and check on it.
But go fix it with magic air.
So if you take a can of compressed air and you flip it upside down like they tell you not to, you can use it like a freeze spray to make things cold.
And it's going to spray on the comparator. And it's fixed.
Look at that, it works now.
So, and actually the comparator runs hot, so I think the comparator is toast. Right now it's completely frozen, right? It's this guy over there.
Very frosty.
Very frosty. It works, and eventually it will warm up and it will not work anymore. Alright, so now I have to look if I have an old comparator. No, I do. I have some old ones too that were used in core memory.
The drugs are kicking in.
It's not looking good. So we were looking at trying to find replacements for the 710, but it turns out I have one. It's disguised as a Fairchild part number, but these comparators were developed originally for core memory. They were the earliest ICs, analog ICs. And so it's a sense amplifier. So this is a 710. I used it actually in my core memory videos to make sense amplifiers. So that's what that is. We'll replace it with that. Okay, new comparator in it. Looks very similar actually. It has even this little spike at the end. And then if I increase the frequency, oh man, it does this. It's the same! No, that's incredible. It's exactly the same.
Look at that.
It's exactly the same.
Did you already try the cool down trick?
No, I haven't. But I suppose it'll do the same thing. Yeah, it's less sensitive, this one. I have to get it exactly the right temperature.
No, it's just cooling off.
So that's not it. We were led astray by the temp experiment. It would only make things slightly better until we bumped the frequency slightly higher, and then it would be just the same. The fault was elsewhere and quite elusive. Okay, we have been bothered by this oscillation problem for the whole afternoon, and we couldn't make sense of it. But I think we found the smoking gun. So we see oscillation and we think, okay, something's going too fast, too much gain at high speed. So we try to slow it with capacitors, filtering, whatsoever. Can never get rid of it, it gets worse. So what happens is we see that oscillation at the output of the comparator when it gets to the bottom. The smoking gun was that the capacitor decreases and then it stays down, and it should not. It should continue to go down until the threshold voltage changes. So we kind of looked at the output of the threshold voltage, and it looked correct. So it's still a little bit noisy, but the capacitor should continue to discharge. Let's freeze on this for a moment. We had seen in the previous episode that in this integrator arrangement, the square wave at the input, in green, controls the triangle wave at the output, in yellow. But it does not. But that cannot be in a circuit that is that simple. The output must be the integral of the input, which led us to the answer. Maybe our green curve was not controlling the integrator as directly as we had assumed. And we couldn't understand that until we looked at the schematic. And my green trace that controls the threshold is from here. And that's the one that says whether a capacitor is going to go up or going to go down. But the way they control it, there are two paths. There's one path that goes and charges and discharges the capacitor, and there's another path that controls the threshold of the comparator. And if those are not changing at the same time, the circuit is not going to work. We had assumed they were the same thing. So now we looked at the two paths, and remember I changed the transistor in that path. And that's the one that's controlling the capacitor. The charging, discharging, and then the comparator goes down to 0, but my new transistor is too slow. It doesn't go up. This fault is utterly devious. I'll need to explain this with a bit of elevator music. So our circuit is based on a simple analog integrator. We put a square wave at the input and we get a triangle wave at the output. If we want to make it faster, you'd think we could just make the driving square wave faster. But there is a problem with that. Since we'd give less time for the capacitor to charge, the amplitude would be lower. So that's not what we do. Instead, we control the charging rate of the capacitor with a variable resistor. We keep the amplitude constant by checking the triangle output with a comparator. This is what our 710 comparator does. The comparator will switch the integration direction when it hits either rail. But wait a second, we have two levels to compare to, but we were very cheap and used only one comparator. So we use a trick. We feed back the output of the comparator to its reference input. This will generate the two reference levels we need, comparing against a high voltage when charging up and a low voltage when charging down. Very clever. But our excessive cleverness is about to bite us in the butt. In the circuit, the comparator connections are not direct. Each of the branches goes through a separate buffer implemented by a bunch of transistors. And I probably made the reference level one slightly slower than the other with my replacement transistor. So let's see what happens now. This is the part where the triangle wave is going up. The output soon hits the high comparison point. The comparator toggles as expected, and both branches switch to low. Now the triangle wave is going down, and so far everything is going according to plan. Eventually we hit the low comparison point, and that's where things go awry. The comparator toggles again, but while the integrator driving buffer goes up, the reference level lags behind by just a little bit. It stays low for a very short instant. So now the triangle rises again, but since the comparison voltage has not switched yet, it immediately crosses it again. The comparator goes low again, the triangle wave goes down, and it crosses the low level immediately again. And the cycle repeats. The reference level buffer never has enough time to catch up. So we get a fast oscillation. This is extremely unusual. Audio frequency circuits should not be so sensitive to which transistors you use. And my replacement one is no slouch by any means. It has a transition frequency of 250 MHz, matching the original. But this circuit is incredibly sensitive to variations in the transistor turn-off time. If the two buffers do not switch at exactly the same speed, it becomes unstable. So it turns out the little transistor that I replaced is a vintage speed demon. It's 18 nanosecond turn-off time, and the one I replaced it with was listed as the same frequency transition to 50 MHz, but the turn-off time was much longer. So I stole this one, put it here, and I put my new transistor over here. And it doesn't matter as long as the transition in threshold happens before the transition, the reversal of the charging of the capacitor, it should work. So what I did is that I took the 5134 from that was over here and replaced it over there and put my slightly slower transistor over there. So I have now exchanged my two transistors and the things line up almost the correct way. I can go from super slow to really fast. So phew, we got it. Okay, so I'm still not done. I have to repair the power supply and I check all the caps. Capacitors from 1979. Is it still good or does it need to be changed? Electrolytics. Change all your electrolytics. ESR 260 milliohms. Capacitance 4.86 millifarads, and that's supposed to be 4.3 millifarads. How is that for you? No Chinese made capacitors. Oh wait, maybe they are. No, oh, from Garden Grove, California. Good stuff from 50 years ago, still good today. 4 millifarads. After 40 years, they are still perfect. So fortunately, it gives us auditory feedback. If I turn it on, it growls. And I determined that it was this guy that was growling, not this one. And then, since that transistor was hot, I just disconnected this and checked if it worked. Better. Yes, no growl. So it's this little power supply that's bad. There are not that many components on it. I'll probably test the diode bridge next. Okay, diode bridge checks bad. So you check the 4 diodes in the bridge. And That was okay. That was a short bad diode bridge. Okay. I jury-rigged a bridge that I had in my bin of good stuff. And let's see if it still rolls or not. 1, 2. No roll. Okay. At least it passes the audio test. No see. Nothing. So after doing a better soldering job, it works better when it's joined with solder. Alright, 35 volts. Excellent. Alright, we are starting to see the light at the end of the tunnel. So I put it back together once again, and then I discovered I had a few more mechanical things to do, as I had not realized that 3 of the BNC connectors were no longer around and needed to be changed, and 1 of the banana plugs had been abused too. And for good measure, 1 of the switches was not behaving either, just 1 of the 2 outputs of it. Fortunately, all these remaining issues were minor. The switch was a short circuit from a wire end cut too long, either original or because it had moved when I replaced the adjacent switch. The BNCs needed some redrilling to fit the ones I had on hand. Yes, I had protection on the other side to catch the metal chips, and I carefully vacuumed everything afterwards. The banana plug was the most vexing as it was bent, and the nut had jumped the plastic threads and mangled them. I eventually managed to take it out, straighten it up, rethreaded the end with its own nut, and all was well. And the last step is to do the adjustments. They are a million, and that's for the frequency accuracy. So here I should be at 100 Hertz. I am at pretty close, 107. There you go. Hertz. That should be 1 Hertz is 0.997, 10 Hertz, and it's 10.05. 100 Hertz, and it's 100.09. 1 kilohertz, and it's 995.1. Etc., etc. You get the idea. It's not an HP instrument, but it was much more accurate than I expected. So in the end, what did we have to take out of this machine to exercise it? Well, quite a bit of things, a lot of broken connectors, broken switches, broken screws, a bad diode bridge, some broken BNCs, and a whole bunch of transistors. Actually, we changed 7 of them. Now, granted, some are because I changed a differential pair and 1 is my own doing, but still, that's a lot of bad thing in just 1 unit. I think I've done it. I've finished my monster breadboard system, so now everything works. I get my square, I get my sine, it goes slower, it goes faster, it's exactly at the frequency it says it should be. I have my little pulse in the bottom, I can vary the amplitude, I can vary the amplitude of that one, the baseline. I have the power supply which I can adjust, and even my little switch number 7 works, so everything works. Now we can just have fun and make circuits with it. Woo, that was hard. Lots and lots of faults in that beautiful breadboard system. Yay, a happy ending again. Our Monster Elite 2 breadboard is able to rejoin its family with our tricked up DG designer and the simple but elegant BB4 from the same manufacturer. Hopefully we'll make a lot of happy breadboard circuits in the next episodes. See you then!